Okay, so this is a tutorial on the equations for Doppler shift. We are going to write down 3 equations for 3 different situations. The first equation, we will derive the equation for it, and then the other 2 we'll just give, and then we'll do some application problems for each. So the first situation that we want to look at, and the one that we're going to derive, is when we have a moving source of a wave. It could be sound, it could be light. Let's think of an ambulance or a police car with a siren. So let's say this dot represents the object in question, and let's say for now it's stationary. So when it puts out its first wave, the wave propagates out in a ripple, and after a period t, let's say it's traveled this far as designated by the circle, when it's about to put out its next wave. Okay, so the next wave would start here, then after another t, this wave will move to here, and this wavefront will have moved out an equal wavelength. So if we keep continuing this, we'll just get concentric circles of equal spacing that propagate out from the central point. Now let's change the situation to where we are moving, and let's say the source starts moving to the right, and this dot also indicates the source. So again, we have this circle as our initial reference wavelength when it wasn't moving. So from here to here, okay, to the edge of the circle, we'll call lambda. However, if the source is moving, by the time it emits the next wave, the first wave will be here, so there is going to be, so here is the next wave emitted after time t. This one is the original one, and so we see that they're closer together. So the object has moved from here to here in the time t, which is simply equal to its speed, u, multiplied by that period t, and then the wavelength that is observed is lambda prime, okay, which is nothing more than the difference between the original wavelength and the new wavelength, because the source has moved along with the original wavefront. So we can see there's a very simple relationship between the original wavelength, the new wavelength, and how fast the object is moving. So we can write that as lambda prime equals the original lambda minus u, the speed of the object, and the period of the wave. So let's just do a manipulation on this so that we ultimately end up with a new frequency. So the next step is, let's break up the right side of this equation. So this becomes equals, well, lambda in general, using the wave equation, is the speed of the wave, v, divided by the frequency of the wave, minus u, and t is nothing more than 1 over f. So we can call this u times 1 over f, or u divided by f. So that's lambda prime. Let's simplify this a little bit. We got a common denominator, so this is nothing more than v minus f, v minus u, all divided by f, and that again is lambda prime. Now if we take lambda prime and look at it in and of itself, that has to follow its own rules from the wave equation, and lambda prime would be equal to v divided by f prime being the observed frequency, the shifted frequency that we've been talking about. So if we solve for f prime, we see that f prime is nothing more than v divided by lambda prime, and if lambda prime we already established is v minus u all over f, this becomes v divided by v minus u all over f. Okay, and now we can simplify that. The f is the denominator here and the denominator, so it flips up to come on top, f. The v minus u stays on the bottom, and we have v all divided by v minus u. Okay, so again, that's f prime. I forgot to put that right there. So I'll rewrite it right over, or actually I'll put it down here. So we see that v prime, or f prime, is either a fraction or a multiple of the original f. So it's f times v divided by v minus u. Now again, the minus sign comes from the fact that the source is moving towards the observer, and the observer is here on the right. In fact, we can probably put an O there for observer. If the source was moving away from it, then this would become lambda plus lambda ut. The negative sign that is distributed throughout here would become a plus sign, so we would have a plus sign under there if we're moving away. So let's put this down. V is the speed of the wave, or wave speed, and U is the source speed. That's our police car, that's our moving star, whatever the case may be. Okay, and as alluded to before, we have a minus plus in this denominator, so we want to use the minus sign. Okay, if we're moving toward the observer, or excuse me, if the source is moving towards the observer, and then we use a plus sign if we're moving away. A minus sign will make the denominator less than the numerator, which will make this product, or this quotient, greater than 1, so our observed frequency is greater than the original, which we expect from a conceptual standpoint. Alright, so before we apply that, let's look at two other situations. Okay, the second situation is when we have a moving observer. Okay, it's a very similar analysis that we did before, so we're not going to derive that from scratch. But we have an equation that says the shifted frequency, the new frequency, is equal to the original. And now we're going to do V plus or minus U all over V. And again, V is the wave speed, U is the observer's speed. So if the observer is moving toward you, we expect a higher F prime, so we want to use the plus sign. And if the observer is moving away, we expect this numerator to be less than the denominator, so we get a fraction of F, so we use a negative sign there. And lastly, in certain circumstances, the velocity of the source is much, much less than the velocity of the wave. And that wave this usually applies to light, but it can also apply to sound traveling through a liquid or a solid where it goes particularly fast. So instead of solving for a new frequency, F prime, we can solve for the actual shift in frequency. And the shift in frequency is a fraction of the original frequency, where that fraction is V over C. V, in this case, is not the wave speed, it is the speed of the source, so that's a little bit different than here. And C is the speed of the wave, and it's usually the speed of light. But again, it could be the speed of a very fast-moving sound wave, especially if that speed is much greater than the source itself. Okay, so let's apply this to a few situations. Right. So our first problem is we have a car traveling at a constant speed towards a stationary observer. So we have toward, and we have our source of sound is moving. Okay, the stationary observer is not moving. So we're given the frequency, and we are giving what the person hears, the shifted frequency. So this would be, whoops. Okay, so this would be F prime, and this would be F, the 660 hertz, and the speed of sound is given as 330, and that is our V. So the hard part about this is just determining which form of the equations we want to use. So we've already established we have a moving source. So our equation is F prime equals F, and we have V over V minus plus U. Since we are moving toward, we're going to use the minus sign for U, and now it's just an issue of plugging in the values given. So if I solve for, we're looking for U here, how fast is the car moving? Okay, we could say V minus U all over V equals F divided by F prime, if I've done the algebra right. Okay, so let's say then that V minus U equals V times F over F prime, and therefore U is going to be equal to V minus V F over F prime. Okay, if we do it all algebraically first, we can plug in the numbers. We have 330 minus 330 times the ratio of f to f prime, 660 over 720. Alright, and if we plug the numbers in and do this correctly, we should get an answer of about 27.5 meters per second. Okay, so the car is obviously moving slower than the speed of sound, but not so significant that we would need our approximation equation. Alright, let's look at a little bit more complicated problem. Alright, we have a bat emits a high frequency sound directed towards a cat, in this case, that is running toward the predator, unbeknownst that it's being monitored. We want to know what is the frequency of the reflected wave. So this 5,000 kilohertz or 5 kilohertz wave hits a cat, bounces off the cat, comes back to the bat's ears. Now what makes this a more difficult problem is there's going to be two Doppler shifts. One for the cat is going to observe a frequency, even though it doesn't realize it is observing it, of a higher frequency, and then that higher frequency is what bounces off towards a moving object. That, in that case, the bat. So we're going to apply the Doppler equation twice. One for a moving observer and one for a moving source. Okay, so let's do the moving observer one. So we are expecting a higher frequency, so let's call this f prime, but we're going to give it a subscript 1 because that's going to be used in the next situation, is going to be equal to f, the original frequency. And since this is a moving observer, we're going to do our v plus u. Right, toward is the plus sign, all over v. Okay, so that's going to equal the 5 kilohertz times v, which is, I guess we'll take it as 330 meters per second, plus this small adjustment for the moving cat, all over 330. Okay, I guess I won't put the units in there. Plug and chug, and we get 5,053 hertz is what the cat observes. So when that bounces off and heads towards the bat, okay, the cat acts like a moving source. Okay, so our case 2, now we have a moving source. So we would use the moving source equation where we have f2 prime is equal to the emitted wave, which is now f1 prime, what we saw before, and we use our moving source equation, which is v over v minus u. So go back and look at this equation to make sure you understand why we're using this one as a moving source and this equation for a moving observer. So plugging in numbers, we have 5,053 hertz times 330 all over 330 minus the 3.5. So this is going to enhance it a little bit, and plug and chug, and we get 5107 hertz. All right, and that's our final answer. So we got to be careful here that we adjust for the fact that we have a moving observer. In fact, if we were clever, we could do this all in one step. Okay, and if we basically solving for f2 prime again, we take for f1 prime, put this equation in here, and we have f times v plus u all over v times v over v minus u. And we notice that the v cancels out here, and we're given one nice equation, which is v plus u all over v minus u. Now the plus and minus are indicative of they're moving toward each other. If they were moving away from each other, then these signs would reverse. Last problem is more of an astronomical problem, kind of related to what we talked about with shifting wavelengths of light. So we want to be able to detect an Earth-sized planet. and we need to be able to detect the radial velocity. In other words, if you recall, if a planet is orbiting another star, that star is also orbiting a center of mass, and at some points it's coming toward us,